So today I would like to talk more about hazards. Okay, so these hazards are situations that would cause incorrect execution of the instructions in the program. So we have three different types of hazards that we need to be aware of, and we need to handle them in order to ensure the correctness of our pipeline that we are going to implement. So the first type is structural hazards. Okay, I talked about it last time. I will go over the same example briefly today. And we have data hazards. Okay, I will go into the details of data hazards, and also we have the control hazards. So the data hazards are caused by data dependencies between the instructions, whereas control hazards are caused by the jump and the branch instructions. And these hazards complicate the pipeline control, and sometimes if they are not handled properly, they also will limit the performance of the pipeline. So we have seen the structural hazard, okay, last time. This is a situation in which we have two different instructions are trying to access the same hardware resource at the same time. We have seen this example last time. So I have the load instruction. Okay, so the load instruction will go through the 5 stages of the pipeline: fetch, decode, execute. Now it needs the memory stage because it has to load from the memory, data memory, and then write back. So once we have the data, then it can be written back into the register file. In the case of the OR immediate, okay, it has to be fetched. Notice the overlap. So while at clock cycle number 2, while we are fetching the OR immediate, we are decoding the load instruction, which is the previous instruction, is now in the second stage of the pipeline. So we decode, then we execute. Now there is no need for the OR immediate. Now let us say, one designer will say that, why do I need actually to wait until the last stage? Why not write back immediately? Okay, so since we have executed, we have the result of the ALU, we can write it back into the destination, which is T4 in this example. Now, the problem of this is that we have now 2 write-backs happening at the same cycle. We have 2 instructions that would like to write back to the register file at the same time. Notice the load instruction is going to write back to T6, and the OR immediate is going to write back to T4. So now we have a conflict. Okay, so this conflict is called structural hazard. Okay, and this is because we are allowing 2 instructions to write back to the register file at the same time. So that's the meaning of structural hazard. Right. So how do we handle this structural hazard? Okay, we have one of 2 solutions. First, the hazard is serious. Yani we cannot ignore it. We have to do something about it. Okay, so solution number 1 is to delay the access to the resource. Okay, that's solution number 1. We delay the access, okay, to the resource. It means we must have a mechanism to delay the instruction to access the resource. In our example, we have seen that the resource here is the register file. So we want to write to the register file. So we can force all the write-backs to take place in stage 5. Okay, that's delaying the access to the resource. And if we do it, already we have done this before, okay, when I introduced the pipeline. So this can be eliminated by design. So the way that you design the pipeline, you can eliminate the structural hazard by delaying all the write-backs to be done in the stage number 5. That will be a good solution because we are fetching 1 instruction and then we can write back, okay, 1. We don't need to write back 2 instructions at the same time during the same clock cycle. So we delay the access to the stage. So we delay the write back to the stage number 5. Now, if you have an ALU instruction, okay, so what does it do in the memory stage? It will do nothing. Okay, so basically we are delaying its access. So the ALU instructions are going to bypass stage number 4, which is the memory stage, without doing anything. Okay, so that would be a good solution, and that will resolve the structural hazard. There is a solution number 2, which we add more hardware resources, which means that this is more costly, but it is a solution. So we can have 2 write ports. Yani we allow 2 instructions to write during the same cycle to the register file. So we can use a first write port, okay, to write the ALU result in stage number 4, and we use the second write port, okay, for the data when we load the data. So we do it in stage number 5. Now, in some advanced CPUs, in which we can, let us say, execute more than 1 instruction during the same cycle, it makes sense, okay, in more advanced CPUs is to have 2 write ports so that we can write back the result of 2 instructions during the same clock cycle. But in our simple pipeline, this will complicate the implementation of the register file, because we need 2 write ports, because 1 write port is not sufficient. We need 2 write ports. And if we would like to allow the load and the or immediate, okay, or any load and or any ALU instruction, okay, to write back during the same clock cycle. So 1 will write back in stage 4, 1 will write back in stage number 5. So we need more than 1 bus W. We need actually 2 bus Ws, okay, because we're going to write 2 results, and we need actually 2 destination registers. So this means that we need now to change the implementation of the register file to allow to have 2 write ports. Now, is it actually something which is needed in our simple 5-stage pipeline? The answer is no. Why? Because if we are fetching only 1 instruction, so there is no need to complicate the implementation. Since we are fetching 1, we can actually complete 1 without impacting the performance, okay, of the program. So so for this reason, okay, solution number 1 is better than solution number 2 in our 5-stage pipeline. And there is no need to add more hardware resources, because we're not really fetching 2 instructions. If we were fetching 2 instructions, then we need actually more read and write ports, okay, for the register file. But here we are only fetching 1 instruction each cycle. So, okay, 2 read ports, 1 write port will be sufficient, and there is no need to complicate the implementation of the register file. Right. I talked about this example last time. So let me move on to the second type of hazard, which is called the data hazard. Now, data hazards are related to dependencies between instructions. Okay, so we have 1 instruction depends on the result of a previous instruction. Let me give you an example. We call it read after write, and this is known as data dependence. Okay, so it's called read after write, or RAW. So this is read after write hazard. This is the type of hazard which is caused by data dependence. So compiler writers, they recognize this as a data dependence. So we have 2 instructions, instruction I and instruction J. Notice that instruction I is writing to S1. Sorry about this. So instruction I is writing to S1, whereas instruction J is reading S1. So clearly here we have a data dependence. So we say that J depends on the result of I. Okay, that's a data dependence, and this actually happens a lot in programming. So when you are writing a program, okay, you might actually have a sequence of 2 instructions in which the next instruction depends on the result of the previous one. Now, why is this a hazard? Now, that's a data dependence. But in the case of pipelining, it becomes a hazard. Why is this a hazard? Any idea?
The result has not been computed in S1, and we need it for the subtraction.
Yeah. So yeah. Yeah.
I think you will read and write at the same time to the register. S1.
No, not necessarily. In fact, in the case of pipelining, okay, we are writing to S1 in the last stage of the pipeline. So the instruction has to go through the 5 stages and to write back during the last stage. But for the subtract instruction, When do we read S1? In what stage?
The first stage.
No, the first stage is the instruction fetch. So we fetch the instruction during the first stage. So when do we read S1?
Second stage.
Yes, in the second stage, in the decode stage. So after we have fetched the instruction, then we read S1. So here is the problem. Okay, that's an example. Now here I'm showing that the first instruction here I'm showing S2. Okay. Now notice that the first instruction is going to compute S2. So it's going to write the result. It's a subtract instruction, and it's going to write its result in S2. So suppose that initially the value of S2 is 10. Okay. And now the subtract instruction is going to compute a new value for S2, and the new value will be 20. But the subtract has to go through these 5 stages of the pipeline. So this is a graphical representation. So at the clock cycle number 5, so at the clock cycle number 3 is going to execute. So at the clock cycle number 2 is going to read T1 and T3. Is going to read them from the register file. Then at clock cycle number 3 is going to execute and compute the new value of S2. And at the clock cycle number 5 is going to write the result into the register file. So the value of S2 will be updated at the end of clock cycle number 5. So therefore, the new value will be present at clock cycle number 6. So notice that the new value is 20, and it will be available at clock cycle number 6. Now, let us take a look at this add instruction. So this add instruction wants to read S2. So it's going to be fetched, the instruction, we fetch it from the instruction memory at clock cycle number 2. And then it's going to read S2 and T5. It needs to read 2 registers. So it's going to read S2 and T5 from the register file. Now, there is no problem reading T5 because the subtract instruction did not really compute a new value for T5. The problem with S2. So notice that here S2, so the add instruction depends on the subtract, and it wants to read S2. Okay. And because it's reading S2 at clock cycle number 3, it's reading it before it has been written. Okay. So remember that we would like to write back into the register file in the last stage of the pipeline. That's what we are doing, right? So we are actually writing back to the register file in the last stage of the pipeline. But we are reading the registers. So here, for example, S2 is being read at clock cycle number 3. So this is in the second stage. So after we fetch, we decode and we read the registers from the register file during the second stage of the pipeline. So because of this, okay, the add instruction is not going to read 20 that was calculated, is going to read 10. So if we do nothing, then the add instruction is not going to read the result that was computed by the subtract, is going to read a wrong result. Okay, and therefore, if we allow this to happen in the pipeline, then the program is going to produce incorrect results. Now notice that the OR instruction, this OR, is also wants to read S2. So first we fetch the instruction at clock cycle number 3, and then during clock cycle number 4, because of pipelining, right? So at clock cycle number 4, we are going to read also S2, and therefore the value of S2 is still 10 because we did not the subtract instruction did not update, okay, the S2 inside the register file. So again, the OR instruction, now that's not actually the next, it's actually the second next, is also reading the wrong value of S2. The third next here, the AND instruction, it also wants to read S2. So notice that here the AND instruction is going to fetch at the clock cycle number, it will be fetched at the clock cycle number 5, sorry, at 4, and during clock cycle number 5 is going to read the value of S2. Now notice what's happening at clock cycle number 5. The AND would like to read S2. The subtract is writing S2, but basically the reading and the writing happens at the same time. So therefore, the reading will take the output of the register. Now the reading is going to have the new value at the input of the register. So the register has not been written yet. So the writing will take place at the edge of the clock cycle, at the end of the clock cycle. So for this reason, also the end instruction is going to read the wrong value of S2. So we have 3 instructions appearing after subtract that are going to read the old value of S2, not the new value that was computed by the subtract instruction. Now notice that this store wants also to read S2, but since it's going to read S2 here at clock cycle number 6, that's going to read the correct value of S2. So this only the store instruction that appears here late in the program is going to read the correct value of S2, while these 3 instructions that appear immediately after subtract are going to read the old value of S2. So this is the meaning of data hazard. It's caused by data dependence, and it is caused by pipelining. So we have a data dependence, and in the pipeline, we are waiting until the last stage to write back the result. Of course, we can write it. We cannot write it back early because we have to compute the ALU result, and then we have to wait until stage number 5 to write it back. So notice that here, okay, what is really happening, okay, for the add, for the OR, for the AND, okay, so these are going to read the old value of S2 from the register file, and these will get the value of 10, which is the wrong value. They are supposed to read the new value that was computed by the subtract instruction. They are supposed to read 20. Okay, so if you are executing these instructions serially, one at a time, then the subtract will write back its result, which is 20, and all the instructions after that are going to read 20. That's what the programmer, okay, has in mind. So the programmer has computed a new value in S2, and the programmer actually wants all the instructions that appear after the subtract to read the new value of S2, not the old value. Okay, and pipelining is creating a problem. So this is called a data hazard. All right, is this clear?
Yes.
Yes.
Right. Okay, so how do we resolve it? How do we resolve this problem? How do I eliminate this data hazard?
I think first we need to check if the operand of the next instruction is is used in the first one. Like here,
Yes.
the S2, because sometimes we don't have this. Sometimes it's not always dependent.
Right. So first we have to detect if there is really a data dependence, right? So really we have to detect if we have a read after write, and we can design the logic in the pipeline to detect that we have a read after write. Yes, I agree. So we need to detect this. Like, okay, so if we detect this and we have that, we have a data dependence, we have a read after write, what do we do?
Delay 3 cycle.
Yes, that actually is a possible solution. Yes. So what we can do is that we have to delay reading from the register file. So if I delay add instruction here, I actually stall the pipeline. It's called stalling the pipeline. So let me talk here about a solution here. So notice that in the case of the store, we are reading the correct value, but for the 3 instructions, so we are only worried about the add, the OR, and the AND. Okay. So one solution is called actually stalling the pipeline. In other words, first we detect. Like you said, we have to detect, because if there is no read after write, there is no problem. We can just read early in the pipeline. But the problem is when we have a data dependence. So first we have to detect that the add instruction depends on the subtract. And this can be done easily. I will show you how. Okay, so we need to add logic, extra logic in the pipeline that will detect that the add instruction depends on the result of the subtract. Now, this is based on the register number. So this is S2, this is S2. So basically inside these instructions, we have fields. So these fields indicate the register numbers, and we can just match. So if the source here, so that will be RS, this will be RD. So we look here at RS and the RD fields inside the instruction, and if they match, they are exactly the same register. So in this case, we say that we have a read after write. So that's a data dependence. Now we cannot read at clock cycle number 3. So notice that here, okay, the add instruction wants to read at clock cycle number 3. We cannot allow it to read at clock cycle number 3. Why? Because this is not going to read the value that was computed by subtract. It has to read the value that was computed by subtract. Okay. Otherwise, the program will produce incorrect results. So it has to read the new value, not the old value of S2. So we have to wait until clock cycle number 6. So what we need to do is that we need to stall the pipeline. This is called stalling the pipeline. It means that we keep the add instruction. We keep it in the second stage of the pipeline. So it's still in the second stage. We cannot allow it actually to execute. Okay, so we have to wait until the clock cycle number 6. Then it can read the correct value, which is 20, after it has been written by the subtract. So the subtract is going to write at clock cycle number 5. So the new value will be 20 at clock cycle number 5. Okay, so it's going to write the value of 20. So the new value will be available here at the input of the register 5. So the new value, which is 20, will be available present at clock cycle number 6. So once we have written it, then it is safe to read from the register file at clock cycle number 6. So now we have here 3 stall cycles. So notice that we are delaying, okay, the add instruction by 3 cycles. And the reason why we are delaying so that it is safe to read the new value, which is 20 at clock cycle number 6. And because we are delaying the add instruction, so the add instruction is going to wait in the second stage for 3 clock cycles, then the OR instruction cannot be fetched. Okay, it cannot be fetched during clock cycle number 3, 4, and 5. So we should not really change the program counter. So we have to freeze the program counter for 3 cycles before we can fetch, okay, the OR instruction. Okay, so the OR instruction is going to remain in the first stage of the pipeline. It's not really going to actually, we're not going to advance the program counter. So if the second is, so the add instruction is in the second stage of the pipeline. So the OR instruction that comes after it will remain in the first stage for 3 cycles. So this is called the stalling the pipeline, and we need 3 stall cycles. So we need 3 stall cycles during clock cycle number 3 through clock cycle number 5. Stall, stall, stall. And this is wasting 3 cycles. We are wasting 3 clock cycles because we are not doing anything, and this is going to reduce the performance of the pipeline. So by stalling, it means that the instructions are not really moving in the pipeline, and therefore this is going to increase the execution time of the program, and this is going to reduce performance. Now, the way to implement this is that we need to insert bubbles. So when we stall the pipeline, what will happen in the execute stage? Basically nothing. So we just insert bubbles, and these bubbles here, 3 bubbles, because we have 3 stall cycles, these are no operations into the ALU. So basically we just insert bubbles, and these bubbles are just no operations, okay, that basically have no impact on the pipeline. So the add instruction is going to remain in the second stage until clock cycle number 6, and the OR instruction that comes after the add is not going to be fetched until clock cycle number 6. That's the solution number 1. Okay. Right. So this will complicate, definitely, it's going to complicate the implementation of the pipeline, and it's going to reduce performance. Can we do better than solution number 1? Can we have solution number 2? Can we do it in a way without stalling the pipeline? Is there a better way to solve this problem?
I think if we detect a dependency, can we start the next instruction? Can we modify the program counter to start, and then we come back? I don't know if that. I mean, we start with add, then, no, sorry, okay.
We have to fetch these instructions in program order, right? So the instructions appear one after the other in the program, and therefore when we increment the program counter, we fetch the next instruction. So we fetch the add, and then we fetch the OR, and so on, right? Somebody has raised his hand. You have actually somebody would like to suggest a solution. Yes.
I was gonna say that we can skip a line, like, but it's not.
You cannot skip. You have to execute. You have to fetch. You have to read from the register file. So the add instruction, the OR, all of them have to be executed. You cannot be skipped them. Okay. So basically, the CPU is implemented. The pipeline is to fetch and execute instructions. Okay. Now the observation is like this. The observation is that the subtract is going to compute its result during clock cycle number 3. So when it executes, it does the addition. So the ALU is here, right? So the observation is somebody will observe that, okay, when do we have this new result, this 20? This 20 is computed by the ALU. It's at the output of the ALU at the end of clock cycle number 3. Okay, so why wait until clock cycle number 6 to read the value 20 from the register file? So the idea is called forwarding the ALU result. Forwarding is a much better solution than stalling the pipeline. And the idea is like this. Again, I have the same program here. So this is the subtract, which is going to calculate S2. And this is the add, which is going to read S2. So now notice that the subtract is going during clock cycle number 3. Now the value in the register file is still 10. So if you read S2 from the register file, so for example, this add, if it wants to read the value of S2 from the register file, it's going to read the value 10. However, okay, we have the subtract has computed the value of the S2, and the value 20 appears here at the output of the ALU. It has not been written yet into the register file because the write back stage is stage number 5. So we have to wait until stage number 5 to write it back. Of course, the subtract is going to bypass the data memory without doing anything. And then it's going to write back. And by the end of clock cycle number 5, we have updated the register file and we have the new value in, which is 20. Okay, it will be available at clock cycle number 6 inside the register file. But we're not going to wait until clock cycle number 6 to read it from the register file. I'm going to use the concept of forwarding. I'm going to take the result from the output of the ALU and feed it back to the input to the ALU. So basically, we take the output of the ALU and we feed it back to the input of the ALU. So we need to have now an extra bus, okay, or more than one bus, in fact, inside our pipeline that allows the output of the ALU. Notice this actually here, this red line here indicating that the output of the ALU is fed back to the input of the ALU. Now, this is the first input of the ALU here, right? And this is because S2 is the first source operand. So basically, we have to detect that we have read after write. So here we have a read after write, and S2 is my first source register. It's RS, not RT. And for this reason, we have to feed back the output of the ALU back to the first input of the ALU. So this is called forwarding the ALU result. Now notice that the OR instruction, which is the second next, also it wants to read S2, but this is RT, not RS. It's the second. But by the time it wants to read it, notice that here, so there is no stalling of the pipeline at all. We are not even stalling. We are not really wasting any clock cycles. Now, the subtract instruction is now in the memory stage. Okay, so by the time the OR instruction has reached the second stage, of course, still the value is old, it's 10. So if it's going to read it from the register file, it's going to read the old value of S2, but that's okay. It's not going to use the old value, it's going to use the new value of S2, and therefore we forward. Now, notice that the new value appears here. That's the new value of S2. It appears here. That's the ALU result. So this ALU result appears on this bus, and therefore we can forward it back to the second input of the ALU so that we can execute the OR instruction at clock cycle number 5. So we did not delay the execution. Okay, we forwarded the ALU result back to the second input of the ALU, but now we forwarded from the memory stage into the ALU stage. And therefore we were able to execute without delaying. So we don't delay, we don't stall the pipeline. The same thing for this AND instruction. Notice that the AND also wants to read S2. So again, it's going to read the value of S2 from the register file. It's going to read the old value. But that's okay. We are going to forward. So now we forward S2. Notice that I'm forwarding now the value of S2 now, it's 20 here, available at the input of the register file. So we take it from the input and we forward it here to the second input of the ALU because S2 here is RT. Notice that this store instruction, okay, wants to read S2. Before that, notice that this AND instruction also depends on the OR instruction. Notice S6 here, okay? So the OR here is writing S6 and AND is reading S6. So we have another data dependence. So because we have another data dependence, so the OR is going to compute the result of S6 at the output of the ALU, and then we feed it back also. So we have two forwardings. So during this actually cycle, we have two forwardings. We are forwarding the value of S6 as well as the value of S2. Now for the store instruction can read the value of S2 directly. Okay. So it can read the value of S6 directly during clock cycle number 6. So there is no need for forwarding because already we have the value written inside the register file. So that's really the idea of forwarding, is that there is no need for bubbles. There is no need to store the pipeline. What we have to do is that we have to keep track of where is my ALU result. And then we have to feed it back either to the first input or to the second input of the ALU. Khalid? Yes, Khalid, تفضل. Khalid, your hand is raised. Do you have a question?
Can you hear me now, Doctor?
Yes, I can hear you. Yes.
The problem with this solution, I think, is it is specific to this situation. If we have another instructions that depends on each other, we might have a problem, right?
Well, we are going actually to resolve all the problems. Okay, not only for this situation. In fact, it does not really matter what ALU instruction you have, okay, what registers you are used. We are going to handle actually all data dependencies. They are going to be resolved, and all data hazards are going to be resolved. Like, let us see how we resolve that, how we implement this. Okay, so this is just one example, but the solution is going to apply to any situation. So that's what we are going to do. So how do we implement this forwarding? So the trick here is to take the output of the ALU and to feed it back to the input of the ALU. So we're going to introduce two multiplexers. Okay, in order to implement forwarding, I'm going to introduce two multiplexers. Now notice that the first input to the ALU, that's my first ALU input, it's A. Typically we read it actually from bus A, and we put it here on the, so that's actually bus A, that will be A. So when we read the value from the register file, it will be available on bus A. So this will be the value of register RS. And bus B here will be the value of register RT. So RS and RT, these are the fields that appear inside the instruction. And therefore their values, okay, will be available on bus A and bus B. It can be any two registers. It does not really matter. Now, if there is no forwarding, so notice that here I have a multiplexer. It has 4 inputs. I will tell you why we have 4. This is a 4-to-1 mux. So input 0 here, it means that there is no forwarding. Okay, we just take the value on bus A, and this is actually my first input A, and we use it in the next cycle to execute. The same thing here for bus B. Fine. So now, suppose that we have detected that we have a data dependence. So if we have a data dependence, okay, the instruction which is executing in the ALU will have its result here at the output of the ALU. We need an extra bus, which is shown here in green. So we feed it back here to input 1. So in other words, even though we are reading the value of RS and RT from the register file, we're not going to use them. These are the old values. And we take here, we feed back the output of the ALU back to A and back to B, depending, of course, if we have a data dependence or not. So here we have a choice to select. So this is why we have these multiplexers. Now, if this actually means that the instruction depends on the previous. So if I have an instruction here, look at this instruction register here, okay, in the second stage of the pipeline. I'm not showing actually here the first stage because it's not really important for us. For forwarding, the focus will be on the second stage and the third stage. So we have the second stage, which is the decode stage. So here during this instruction, we decode the instruction. During the second stage, we have the instruction, we have RS, we have RT. We also have RD, okay? So we have these registers. And we can look at the RD2, RD3, and RD4. Now, these are the destination registers of the instruction which are in the program, okay, that were actually previously in the program. So if my instruction here is in the second stage, my previous instruction will be in the ALU stage. And my second previous will be in the memory stage, and the third previous will be in the write back stage. Right, so what we have to do is that if there is a data dependence, we have to forward from the ALU back to A and back to B, which are in the second stage. We can actually have a dependence on the second previous. So we can take it from the memory stage back to A and back to B, or we can take it from even from the write back stage. So this is the write back, this is the data on bus W. We can feed it back to A and back to B. So we need two control signals. Every time we introduce a multiplexer, we have to control these multiplexers. So the first one is called forward A. It has 4 possible values. So my select here consists of 2 bits. So either 0, 0, it means 0, or 0, 1, or 1, 0, or 1, 1. Okay, so these are the 4 possible inputs to this multiplexer. The same thing for forward B. So now we need to generate forward A and forward B to control the selection, okay, for these 2 important multiplexers that will implement forwarding. So the meaning of the forward signals is that if I choose forward A equal to 0, it means there is no forwarding. It means that the first ALU operand comes from the register file. It's the value of RS. So back here, if I select 0, it will be just the value on bus A. It means there is no forwarding. Just take the value from the register file. If there is no data dependence, there is no need to forward. Okay. So that's the meaning here of 0. If I select 1, if forward A equal to 1, it means I would like to forward the result of the previous instruction from the ALU stage. Okay, so that's the meaning of 1. Okay, so we are forwarding the result of the previous instruction. 2 means that we are forwarding the result of the second previous, which is in the memory stage. And 3 means that we are forwarding the result of the third previous, which is in the write back stage. So we have actually, these are all the possible, okay, control signals actually for forward A. Either 0 means there is no forwarding. 1, it means that the previous instruction, which is in the ALU. 2 means the second previous, and 3 means the third previous. Okay, so these are in different stages. The same thing for forward B, but rather than forwarding here to the, so again, 0, 1, 2, 3 for forward B. So 0, there is no forwarding. 1 means that we are forwarding to B. So in the case of forward A, we are forwarding to the here to A, which is the first input of the ALU. And in the case of B, this is a second multiplexer. We are forwarding to B, which is the second input to the ALU. Okay. I have an example that explains, okay, how forwarding works. So let us take a look here at, okay, these 3 instructions. So I have load, I have or immediate, and I have subtract. Okay, so this is my sequence. Now, clearly, you can see that here, this subtract instruction depends. So we have T4. So this subtract depends on the load, and this subtract depends on the or immediate. Okay. So you can actually come up with any example that you want. Okay. So notice that the subtract here depends on the or immediate, which is the previous. And the subtract also depends on the load instructions. So these are the instructions in a program order. Now, suppose that the subtract instruction is now inside this instruction register. So this is my instruction register. Already we have fetched the subtract. Where is the or immediate and where is the load word?
Third and fourth stages.
Yes. So remember that here the instructions are fetched in a program order. So by the time we have fetched the subtract, already we have the or immediate. So if the subtract is in the second stage of the pipeline, the or immediate will be in the third stage of the pipeline. So you have to understand pipelining. I talked about this actually in the previous lecture. So the subtract is now here in the second stage. The or immediate will be in the third stage, in the ALU stage. And the load word is in the memory stage. So already we have them in the pipeline. Okay. So the previous instruction will be in the next stage, and the second previous will be in the second next. Okay. So again, this is very important to understand. So by the time we have the subtract instruction here in the decode stage, already we have the or immediate in the ALU stage. And I have the load word in the fourth stage of the pipeline, because these instructions have been fetched before the subtract. So already they are in late stages of the pipeline. So you have to keep track of timing. That's basically a simple thing that you have to keep track. Where are the instructions in the pipeline? Right. So now all the detection takes place in the second stage of the pipeline. So we're going to have a logic here that is going to detect that we have a read after write. So how do I detect? How do I detect? I need to detect that we have a read after write. How do we detect this? It is simple. Look at the register numbers. So here I have RS, here I have RT, here I have RD. Okay. So these are the register numbers. So how do I detect, okay, read after write? You look at these register numbers. Okay. So now RS in this example will be T4. RT will be T7. But what is really important is that RD, okay, so here the output of this multiplexer is going to determine what's the destination, either RT or RD. Okay, so this is RD2. So what is RD2 in this example? What is RD2? If you look at the output of this register RD2, what's the value of RD2? It is just a 5-bit register, by the way, because it's storing a register number. So RS is 5 bits, RT is 5 bits. These are not really 32 bits. Bus A and bus B are 32 bits. But RS and RT, notice that I'm showing them. Okay, this is actually like a small arrow here. These actually are 5 bits. Okay, so RS in this example, RS is T4, RT is T5. But what is RD2? What is RD2?
T7.
Yes, thank you. It is the destination of the previous instruction, which is in the ALU stage. Because when the or immediate was in the second stage, already we have determined that its destination is RT, which is T7. Okay, and therefore in the next cycle we have moved the instruction into the ALU stage. So RD2 is T7. What is RD3 in this example? What's RD3?
T4.
Yes, thank you. So that's also is the target for the load word. So we already have them in the pipeline. So what I need to do is that I need to compare this RS and RT against RD2, against RD3, as well as against RD4. I'm not showing here anything, any instruction, but we could actually also have a data dependence. You could actually have an instruction before the load. Okay, so if it appears before the load, it will be now in the write back stage. Right. So now tell me, what is forward A and what is forward B? How do we control these multiplexers? Now, if I read the value on bus A and bus B, the value of RS and RT, these will be the old values of RS and RT. Sorry, these will be the old values and not the value that was computed here by the or immediate. and not the value that was loaded, okay, by the data memory. So we have the new value for T7 and for T4. So what should be forward A and what should be forward B? How do we control these multiplexers in this example?
Forward A is going to be compared with RS. We're going to compare RS with RD2, RD3, RD4, and the result is
so what will
1,
be,
2, 3.
I want a specific number. Is it 0, 1, 2, or 3?
0, if they are not equal 0, that means no forwarding. If it's RS equal to RD2, mean forward A is 1.
Yeah, I know, but in this specific example, what do you think the value of forward A should be?
RD2 is T7, and the RS here is the T4. Sorry, yes, T4. Sorry, it's going to be 2.
Yes.
RD2.
It's going to be actually 2, because we have to forward here the data T4 back to A. So therefore we have to select. So therefore T4 has already been loaded now from the data memory. So we're going to forward it from the memory stage back to A. So therefore we have to have forward A is equal to 2. So we take it from the output of the data memory. We have this multiplexer here, right? So we select here the data out from the data memory and we feed it back all the way here to input A. That's basically how it works. How about forward B? That's forward B. What should be forward B?
1. It should be 1.
It should be 1. It should be from the output of the ALU back to B. Yes, that actually is forward B. It should be equal to 1. We took it from the output of the ALU and we fed it back here to the B input, okay? The second input of the ALU. So that's basically it. That's actually how it works. You can actually have any RS, any RT, any RD2, RD3, RD4. It will work, okay? It will work. Right. So for this specific example, forward A must be 2 because it depends on the second previous. So now the load instruction is in the memory stage, so we have to forward from the memory stage back to A. So this is why we have to select forward A to be equal to 2. And in the case of the subtract instruction, sorry, in the case of the forward B, it is T7. T7 actually depends on the result of the OR immediate. So that was the previous instruction. So you can see that here that RT is equal to RD2. So this is T7 and this is T7. So therefore, just forward from the ALU. So forward B is equal to 1 because it depends on the previous, not the second previous. That's actually for T7. So remember, the current instruction is in the decode stage. That's the current. Okay, so it's in the decode stage. The previous instruction will be in the execute stage. It is now executing inside the ALU. The second previous exists in the memory stage. So the previous is in the execute stage and its destination is RD2. The second previous is in the memory stage and its destination is RD3. And the third previous is in the write back stage and its destination is RD4, as we have seen in the previous slide. So we have 3 instructions in the second, third, and the fourth, sorry, in the third, fourth, and the fifth stages, and their destinations are RD2, RD3, and RD4. So we can write an if statement that, okay, so this if statement describes the logic. It describes the logic that needs to be implemented. So first we have the source register RS. So in the case of forward A, we check RS. So we have to check that RS is different from register 0, because if it's equal to register 0 to R0, okay, then in this case there is nothing that needs to be forwarded because R0 is always hardwired to 0. Okay, so for this reason we have to check that RS is different from 0. Now if RS is equal to RD2, and we have register write in the execute stage, because we have register write for each instruction. that exists in the third stage, in the execute stage, memory stage, and write back stages. So if register write is equal to 1, indicating that this instruction is going to write, which is in the execute stage, is going to write to RD2, then forward A is equal to 1. So that's the value of forward A. Now, if it's equal to RD3, if this RS is equal to RD3, notice that I have here else if, because the first if has the highest priority. Okay, so I'll talk about this also, because you might also have a case in which RS is equal to RD2 and RS is equal to RD3. Yani the instruction, which is the current instruction, which is in the decode stage, depends on the previous and the second previous, and maybe even on the third previous. Now, this is unlikely to happen, but if it happens, we use forward A is equal to 1. So the first if is given the highest priority. So this is why we write it as if, else, if, else, if, else. Okay. So if RS matches RD2, so this is the closest instruction. Okay, that was just the previous. Then in this case, we choose forward A is equal to 1. If it's equal to RD3 and we are writing to RD3, notice that we have register write here in the memory stage. Then we use here forward A is equal to 2. Of course, we cannot say forward A equal to 2 unless the first condition is false. Okay, and then if it's equal to RD4, now the previous two must be false in order to reach this else if. Okay, so basically it's like a priority. We give priorities, okay, to these Boolean expressions. And then we have here write back. Okay, we have register write in the write back stage. Then we choose forward A is equal to 3. Now, if all the above are false, we reach the final else. The final else indicating that forward A is equal to 0. It means that do not forward, just read it from the register file. There is no need for forwarding. Now that's for RS. We need to do exactly the same thing for RT. Now for forward B, we check RT. Again, we compare RT against RD2, RD3, RD4. We check if we are writing. Okay, so we have register write here, indicating that we are writing to these destination registers. Okay, then in this case, we can have forward B is equal to 1, 2, or 3. And if all the above are false, then forward B will be equal to 0. Right, so these are my if statements. Okay, my nested if else if statements. Okay, in which we determine the value of forward A and forward B. Okay, do you have any question about this? I have a comment here. So the question is, what would happen if we have more than 3 or 4 instructions that depend on each other? Now, do you mean that actually have okay, more in the pipeline? Okay, then in this case, if we just go back to the previous slide, okay, we know that we only have we can only have, let us say, 1 instruction in the ALU stage, and we have 1 instruction in the memory stage and 1 instruction in the write back stage. So once the instruction has written back, so if the instruction does not depend on the previous or second previous or the third previous, if this was the question, Khalid, right? Then what will happen is that the instruction has already written back its result into the register file. And if it has written back its result into the register file, then that's it. There is no need for forwarding. We can read the data directly from the register file. So the problem exists when an instruction depends on the previous or second previous or third previous, and they are still in the pipeline. But once the instruction has written back its result to the register file and it has completed, okay, if it has completed, then there is no need for forwarding. Okay, because the data exists in the register file, and later instructions that come in the pipeline, they can just read it directly from the register file. So the problem only exists for these last 3 instructions: previous, second previous, and third previous, and this is where we need to do forwarding. Right. So
yes,
okay. Right. So so now we need to implement this in the pipeline. So let me show you now this diagram. So the focus is on the second stage. Notice that how actually I'm showing here the instruction in the second stage. So in the instruction, the instruction has RS and RT. Now these are the source registers. So I'm going to now, this is the main and ALU control. Now we are going to add extra logic. Okay, to implement specifically forwarding. We added these two multiplexers specifically to forward the ALU result, the data from the memory stage, and also the write back data, which is in the last stage of the pipeline. So we are forwarding from stage 3, 4, and 5. Okay, but now we need to detect. So we need extra logic that will detect the hazard. So this is called the hazard detect and forwarding logic. The inputs will be RS and RT. So we take RS and RT, okay, and we feed them as inputs to this logic. So basically we are copying it. This RS will come from here. Okay, that's actually it's RS. Let me just pass it like this all the way to here. Okay, so basically I'm just connecting the wires. I'm showing here RS and RT, okay, as inputs. Sorry about this. This is my mouse. So this is RS and this is RT. Again, I need to clean up this. So our RS here, okay, let me just take it clean like this, like this. So basically it's coming from the RS, this actually RS here, 5 bits here for RS, connecting it to the RS input. The same thing for RT, but I'm not going to draw, khalas, that's it. Okay, so we understand this, right? And what else do we need? What else do I need as inputs for this hazard detection logic? Students, can you tell me?
Resistor write.
I need to actually to check, yes, register write. But before that, what do I need?
RT also.
Well, of course, we have RT here. So RS and RT are the source registers of the instruction which exist in the second stage. So I need to connect this. But what else do I need?
The RD
for this hazard detection logic?
The RDs also? RD2,
Yes.
RD3.
Exactly. I need to know the destinations. Okay, for the previous, second previous, and third previous. So these are RD2, RD3, and RD4. Okay, in addition, I need to check if we are going to write to these. So I need the register write. So I need, notice that how I'm connecting all of them. Okay, RD2, RD3, and RD4. These are the destination registers. Okay, so we take it from the output of RD2. This will be the destination of the instruction, which is in the ALU stage. I take it from the output of RD3, which is the instruction which is in the memory stage, and the output of RD4, which is the instruction in the write back stage. So we still did not really write back yet. We are going to write back at the end of this cycle. Now, notice that I have register write. This is a control signal, okay, which is generated by the main control logic here. Okay, so the main control is going to generate all the control signals, and they are going to be propagated from one stage to the next. So register write, which is shown here, let me use my highlighter again. This register write, which is shown here, this is the register write of the instruction which is in the execute stage. I also have register write. This will be the register write of the instruction which is in the memory stage. And here is the register write, which is the instruction in the write back stage. So we have multiple instructions in the pipeline at the same time, and each one has its own control signal. So we are propagating these control signals from one stage to the next one. So all of these have to be checked as well. And then if the logic, which is shown in the previous slide, the if statement is actually going to be implemented, then this actually logic is going to produce forward A and forward B. That is going to control these two multiplexers. And this is basically how we implement forwarding. So we detect that we have a data dependence. So the hazard is detected, and then we forward. Okay, so this is all done in the second stage of the pipeline. Any question about this? So that's what you need to implement, okay, in your pipeline to support forwarding. So you have to change the data path. You have to introduce here forwarding buses. You have to introduce these multiplexers, and you need logic that will detect the hazard and is going to produce forward A and forward B that is going to control these two important multiplexers. So notice that this actually has been complicated a little bit. Okay, so we have to have this logic in order to ensure the correct operation of the pipeline. Okay. Any questions about this? That's basically here is how we implement forwarding. Fine. If I don't really hear any question, I'm going to move on. Okay, so let us move on to the next topic here. Now, does this solve all the problem? Does really this solve all the problems, all the data dependencies, and does forwarding solve everything? Well, do we still actually have some problems which are unsolved? What do you think? Does it handle all the cases?
Yes.
Well, it will handle most of them, but there are situations in which this forwarding, this hazard detection and forwarding logic is not capable of handling it. Let me talk about this situation. Okay, so there are few cases in which we still have to, so this is not sufficient. Okay, this is necessary, but not really sufficient. Okay, so it does not really handle all the cases. So we have to think about, okay, in which situations forwarding is going to fail. Right, let us take a look here at the load delay. Okay, how do we detect it and how do we stall the pipeline? So sometimes forwarding is not sufficient. Let me talk about this example. In this example, I have a load instruction. So we're going to load to S2. So S2 here is my destination. The next instruction is an add instruction that's going to read S2. The second next is OR, which is going to read S2. Then the third next is an AND that's going to read S2. Now the problem exists. Okay, now already we can detect this. Already we have the hazard detection logic. Already we can detect that we have a data dependence between the add and the load. So we know that the add depends on the load. We know that the OR depends on the load. We know that the AND depends on the load. But what is the problem? The problem is that the load instruction is going to take place in the memory stage. So here it's shown in this timing diagram. It is shown at clock cycle number 4. So this is when we load the data from the data memory. So this is done in stage 4. So we don't really have the data except at the end of clock cycle number 4. It's not like an ALU instruction in which we have the result of the ALU at the end of clock cycle number 3. So there is a difference when you have a data dependence and the instruction was a load. Okay. Now the load here has an extra delay. Why? Because we load in the 4th stage of the pipeline, not in the 3rd stage. Whereas we execute in the 3rd stage. Okay, so the ALU exists in the 3rd stage of the pipeline, but here the load instruction exists in the 4th stage of the pipeline. And for this reason, the load has a delay that cannot be eliminated by simple forwarding that we have seen in the previous slide. But notice that here, okay, we need the data, okay, at the end of clock cycle number 3 here. Okay, so when we read from the register file, of course, the data is old. The value that we are reading from S2 from the register file is the old value of S2. But we need the value which is at the output of the data memory. So before we execute the add instruction, we need this data. But the data is not available until the end of clock cycle number 4. But we need it at the end of clock cycle number 3 so that we start executing the instruction during clock cycle number 4. Now, this is not possible because we cannot really forward backwards in time. It's unlike when we have the data is available at the output of the ALU, where we can forward from the output of the ALU back to the input of the ALU. So in the case of an ALU instruction, the result will be available at the output of the ALU, and this can be available early in the pipeline. And therefore, forwarding was possible when we have an ALU instruction. But when we have this load instruction, and the next instruction, for example, an add depends on the load directly, then we cannot really forward. That's not really possible. So for this reason, we need to handle the load instruction in a special way. Okay, because the load, the data is available at the end of clock cycle number 4. Now notice that for the second next and the third next, for the OR and for the AND, it's okay. We can still forward. Okay, so notice that the OR here wants to read S2, and notice that the data is available at the memory stage. So for the, not for the next, but for the second next and the third next, we can still forward. Okay, from the output of the ALU back here to the second ALU input. I can also forward from the memory stage. So at clock cycle number 5, I can actually forward from the memory stage here back to the first ALU input. So that's actually is possible. Okay, so the only problem exists actually with this add instruction. So for the OR and the AND, okay, because they don't really come immediately after the load. So these are the second and the third next instructions. Okay, now forwarding is possible, but for the add that comes immediately after the load, it's not really possible to forward. So in this case, what we have to do is that how do we resolve this problem? How do we solve this problem? So how do I handle this add instruction?
Delay the instruction one stage.
Yes, that's the only way to do it. So we have to stall the pipeline. If I cannot execute the add instruction, okay, during the next cycle, because forwarding was not really possible, I have to delay. So this add instruction has to wait in the second stage of the pipeline. So this is waiting in the pipeline means stalling the pipeline. That's the meaning of stalling the pipeline. So first we have to detect that we have this type of a data hazard. So this add instruction depends on the previous instruction, but the previous is a load. And because the previous is a load, I cannot really forward immediately. I have to wait for one cycle and then we can forward. Okay, so forwarding is not really possible during this cycle. So during clock cycle number 3, I cannot really get the data. So I have to wait for clock cycle number 4. I have to wait for the data to be loaded from the data memory. So for this reason, we have no solution but to stall the pipeline for one cycle. So let us first detect this type of hazard. This is shown here in this slide. So what I need to do is that I need to detect that there is a, so remember that we always detect this situation in the second stage of the pipeline. So after we fetch the instruction, we have the instruction in the instruction register. So this is when we detect the hazard. Remember that the hazard detection logic exists in the second stage of the pipeline. So first we have to detect that the instruction which is in the second stage depend on a previous instruction. So the previous instruction now is a load instruction that exists in the execute stage. And the instruction, so we are detecting that there is a data dependence between the instruction which is in the second stage and the previous instruction which is in the third stage. And the instruction which is in the execute stage is a load instruction. So therefore, its data will not be available until the fourth stage of the pipeline. So for this reason, we write the condition like this for stalling the pipeline. So now we are going to stall. Now, how do I detect that the instruction in the third stage, in the execute stage, is a load instruction? Well, we can check here the memory read control signal. The memory read control signal is equal to 1. It indicates that the instruction which is in the execute stage, so notice that this control signal is for the instruction in the execute stage. If it's equal to 1, then this is clearly that we have a load instruction which is in the execute stage. And we have forward A is equal to 1 or forward B is equal to 1. 1 means that we have a data dependence. We have a data dependence on the previous instruction that exists in the execute stage. So already we have the forwarding logic that can detect a read after write. Okay, it can detect data dependencies. Okay, and therefore it has detected that the instruction, which is in the second stage of the pipeline, okay, which is in the decode stage, depends on the load instruction that exists in the execute stage. Okay, so here the action would be, we have to take an action, and this is actually stalling the pipeline. I'm going to show you how we implement stalling the pipeline, but we need to stall only for one cycle only, and then we can forward. Okay. Now, in order to stall, to implement stalling, I'm going to show you this in the data path. I'm going to show you the drawing in a minute. Okay, what we need to do is that the instruction, okay, this is actually the instruction that depends on the load, which exists in the second stage. So the load is allowed to proceed in the pipeline. So the load, which is in the executed stage, is allowed to proceed into the fourth stage. So that's going to actually to read from the data memory. But the instruction, which is in the second stage, cannot proceed into the executed stage. It has to wait. It has to wait, okay, because we are stalling the pipeline. So what will happen is that we are going to force a pipeline. We are going to insert a bubble. Okay, so we are going to insert a bubble into the executed stage in the pipeline, and the bubble is just a no up operation. So what happens is that the load instruction, which is in the executed stage, is going to move into the fourth stage. And the instruction, which is in the second stage, is going to remain. This is the depending instruction, the one that depends, okay, on the load instruction. So this is going to remain in the second stage. Now, something has to exist in the executed stage during the next cycle. That will be a bubble. Okay, so this bubble is inserted or injected into the executed stage. And this bubble is just a no operation. In order to inject a bubble, okay, all what we have to do is that we have to clear all the control signals. So as long as an instruction, okay, does not update any register in the register file, and it does not update the state of the pipeline, and it does not really modify any register, and it does not write to the data memory, then therefore this instruction has no effect on the pipeline. So if an instruction has no effect on the pipeline, we call it a bubble. Okay, but here we don't really have an instruction. We are going to actually to inject a bubble. Okay, and the way that we do it is that by clearing the control signals. So by clearing the control signals, by making register write equal to 0 and memory write equal to 0, so basically it will have no effect. Okay, so that's a simple way to implement a bubble in the pipeline. So let us take a look here at how we implement this. How do we handle this? So the load instruction, which is, so we decode this, so we detect. So first we have to detect. Okay, so we detect this during clock cycle number 3. So during clock cycle number 3, already we have fetched the add instruction. So the add instruction is now here in the decode stage, in the second stage of the pipeline, and the load word instruction is in the third stage, in the execute stage. So this is when we detect that we have a read after write. So we detect that the add depends on the load. And also we have detected that the instruction, which is in the execute stage, is a load based on the memory read control signal. So the action would be to introduce a bubble. So the bubble here is just, we are going to stall the pipeline. So notice that this is actually called a stall, and which means that we freeze the PC program counter. We do not really fetch an instruction during clock cycle number 3. We don't really fetch the next instruction in memory. Notice that the load instruction is allowed to proceed in memory stage during clock cycle number 4. But we freeze the program counter. Okay, we don't really fetch a new instruction. And the instruction which is in the second stage, which is the add instruction, is going to remain in the same stage. We don't allow it to proceed into the execute stage because it cannot execute yet. It is still waiting for the value of S2. So this is the meaning of bubble. So as if we are converting this add instruction into a bubble, okay? and we are forcing this add instruction to remain for one extra cycle. So during clock cycle number 4, we still have the add instruction in the second stage, okay, and it's not going to execute until clock cycle number 5. So we are not going to execute the add instruction during clock cycle number 4. We are going to delay the execution of the add, and we are going to delay the fetching of the OR instruction from the instruction memory. So this is the importance of freezing the program counter. And we are going to introduce a bubble into the ALU stage. So what's really being executed is just a bubble. So therefore, it does not really matter what the ALU does. It does not really matter what value is computed by the ALU. It does not really matter what's the ALU result. Nothing is going to be written into the register file. We are not going to change the program counter. We are not going to change any register in the register file. We are not going to write to the data memory. So that's the meaning of a bubble. Okay, it has no effect on the state of the pipeline. So this is just done for one cycle. And after that, notice that this is actually done for one cycle. And then after that, we can resume, okay, the execution of the add instruction. So we don't execute the add during clock cycle number 4. We execute during clock cycle number 5. So that's when we resume. And notice that because we are executing it during clock cycle number 5, so by the end of clock cycle number 4, we have the data at the output of the data memory, and then we can forward it. And then we can start executing the add instruction at clock cycle number 5. So this is an extra complication, okay, which is caused by the load instruction. And that will happen if the next instruction depends on the load. Now, if the next instruction does not depend on the load, there is no need to stall the pipeline. So only when we have a data dependence, okay, and the instruction, okay, depends on the load, then in this case, we have to stall the pipeline. Otherwise, there is no need to stall. Okay, so notice that the OR here also depends on the load, but during clock cycle, okay, so we can forward here from the write back stage back into the ALU. So this is forwarding is always possible. Already we have implemented the forwarding logic. So we can still actually forward, but after stalling for one cycle. Now we can look here at the stall cycles. Okay, let me give you here another example. So suppose here I would like to look at the timing. Okay, so suppose here I have a load instruction that's going to load into S1. So S1 here is my destination. It has to go through the 5 stages of the pipeline. So remember that we load from the memory stage. So we have the data at the end of this clock cycle, which is number 4. Okay, so the data is available at the end of the output of the data memory. Now suppose that the next instruction was also a load. Okay, so notice that we are actually loading into S1 and we are using S1 as an address. Yani we are loading the address from memory and then we are using it in the next load instruction. So we have a load that depends on a load. Okay, this can, if we have handled this properly, all of these can be handled properly. Okay, so the next instruction depends on the load, and you can see that we have a read after write. Okay, so the action would be to stall for one cycle. So this is detected when the instruction is in the second stage. So this is the instruction decode stage. So after we fetch, while we are decoding it, we can actually detect that we have here, okay, our S here is S1, and this is actually is my RD2, that's my destination register. So we detect this while the first load is in the execute stage. And the second load is in the decode stage. So this is when we detect the hazard. And then once we detect the hazard, the action will be to stall. So we stall, it means that the instruction is going to remain for another cycle in the decode stage. And we cannot really fetch the next instruction until the clock cycle number 4. We cannot really fetch any instruction in clock cycle number 3. We freeze the program counter. We don't change it. So therefore, we wait here until the clock cycle number 4 to fetch the add instruction. So this is how I look at the timing. Okay, that's from the timing point of view. Now notice that this add instruction, it also depends on the previous load. Okay, I'm just crafting this example. Yani it's not really something that might really happen in real program. It might, but I just would like to illustrate to you what will happen. Okay, if we have this sequence of instructions. So notice that also we are going to detect. So this add instruction will be in the second stage, this is when we detect that we have a read after write again. So it's depending on the previous. So the instruction here is in the execute stage. That will be actually the previous load. And the add instruction is in the second stage. So this is where we decide to stall again. So when we stall again, the instruction is going to wait. We cannot even fetch the next instruction. Okay, so it's going to wait for another cycle in the decode stage. And therefore, we can only fetch at the clock cycle number 6. So notice that this subtract instruction also depends on the load. It also depends on the add. Notice that we have V0 here, but that's okay because the add itself, the add is an ALU instruction. So we can forward immediately without the need to stall. So there is no need actually for stalling the pipeline, okay, when you go from the add to the subtract. So there is no need for stalling. Now notice the forwarding here, okay, how it's really happening. I'm showing it with green arrows. So we are forwarding from the memory stage back to the execute stage. This is basically forwarding the value of S1. Okay, so if I would like to use here my pen tool, so basically the value of S1 is forwarded from one load to the next load. Okay. Now it's actually forwarded to the execute stage because we would like to use the execute stage for address calculation in the case of a load instruction. Notice that also here we are forwarding from the memory stage, okay, back to the execute stage because this actually needs S2. Okay, so also we have forwarding. So notice that it's happening in the pipeline. And here we are forwarding from the execute back to the execute. And this add here is going to forward, okay, to this subtract. So this forwarding is from the execute to this execute. Now notice that this S2 here, okay, is also needed by the execute. So there is a need to forward from the write back stage to the execute. And this can also is supported by the pipeline. So we are forwarding not only V0, but also the value of S2. So the value of S2 now is being written in the write back stage. So we need to forward it here to the execute stage. Okay, maybe I need the green arrow here also to show forwarding. So there is actually 2 forwarding here, because we are forwarding the value of S2 also to the execute stage, from the write back stage to the execute stage. It's not really shown here to just avoid here overdrawing things. Okay, so that's also, you have to remember that we also have another forwarding arrow here because we are forwarding the value of S2 from the write back stage back to the execute stage. Okay. Right. So we have wasted 2 stall cycles. We have wasted 1 stall cycle, we have wasted 2 stall cycles, and of course this is going to impact the performance of the pipeline. Now let me show you how we can implement all of this. Okay, again here we have to go back to the drawing and we have to do it properly, okay, because we are going to implement this, okay, this hazard detection and forwarding logic, but now we are going to stall. Right. So first we have this hazard detect and forwarding. Okay, so we need to detect data dependencies, and also we have our SRT. We have all the control signals. Now notice that in addition to, so this is RS and RT. These will come from the RS and RT of the instruction, which is now being decoded in the second stage of the pipeline. Also, we have detecting here that if it's equal to RD2, to RD3, to RD4, as before, we are detecting for data dependence, read after write. Also, we have register write, okay, in the third stage, in the fourth stage, and in the write back stage. Okay, so it means that we are writing to RD2, to RD3, RD4. So we have to check this in the hazard detect logic. So this is going to produce forward A and forward B as before to control these 2 important multiplexers. But there is something else I added, which is memory read. Now notice that memory read is now a control input, okay, because this is a control signal. It indicates that the instruction which is now in the execute stage is a load instruction. So not only we are detecting that we have a data dependence, but also we are detecting that the instruction which is in the execute stage is a load instruction. And if it is a load instruction, so we have here forward A or forward B is equal to 1, we cannot really forward. So what we have to do is that we have to stall. So we have forward A and forward B as before, But also we have introduced a stall control signal. Now this stall control signal, if it's equal to 1, it means that the instruction, which is still here in the instruction register, we are going to disable the instruction register. Notice that we have a disable here. Also, I'm going to disable the PC. Yani do not update. So at the edge of the clock, do not change the PC. Do not change the instruction register. So therefore, do not really fetch a new instruction. So we are stalling the first 2 stages of the pipeline. Okay, we are not really fetching a new instruction. We are not really changing the instruction, which is, so the instruction which is in the instruction register in the decode stage is going to wait for 1 cycle. And at the same time, while we are disabling the PC and the instruction register, we are injecting a bubble. Now, what is a bubble? It is just actually an instruction that has 0 control signals. So it's not the instruction itself which is being propagated. No, it's just control signals. So the control signals here, okay, is going to indicate that this is a bubble. So by introducing 0 control signals, so rather than propagating the control signals of this instruction, so these are the control signals which are produced by the main control logic for the instruction, which is in the instruction register. No, we are actually injecting, so we're not really selecting the control signals, we are selecting the bubble. Okay, so if this stall is equal to 1, at this input 1, I'm going to inject a bubble into the execute stage. And of course, once it is executed in the executed stage, it's going to pass through the memory and the write back, and it will have no effect on the pipeline. Okay, so whatever ALU result is computed here, it does not really matter. It's not going to be written back. Okay, so this bubble has register write equal to 0. It has memory read, memory write. All of these are zeros, so nothing will be read, nothing will be written, okay, into the data memory. And therefore, it's going to freeze the PC, so the PC will not change. The instruction register is not going to change. So therefore, it's not going to affect the state of the pipeline. So that's how we implement stalling the pipeline. This is how we stall the pipeline. Okay. Right. So notice that this will take place only for 1 cycle, because next cycle, once we inject the bubble, memory becomes 0, and the condition for stalling will disappear. Okay, because stalling will have to have memory read equal to 1. But once we inject the bubble, then memory read becomes 0, and therefore there is no halas will stall only for 1 cycle, and stall becomes 0. So now next cycle we propagate the control signals into, so the instruction, okay, is going to move. So we stall, and then the instruction which is waiting here is going to move into the 3rd stage of the pipeline with its control signals. Okay, so we allow the instruction to proceed in the pipeline after we have stalled, and then after we have stalled, the load instruction will be in the memory stage. So we can use here forward A or forward B equal to 2 to forward from the 2nd previous. So notice that here, so what we have done is that we have injected a bubble between the load and the next instruction that depends on the load. Okay, I hope this is clear. That's basically how we can deal, okay, when we have a data dependence on the load instruction. Now we can actually here use the compiler. Okay, so the software here can avoid, okay, stalling the pipeline, because stalling the pipeline is going to reduce the performance. Right, so we can here use the software, okay, to improve the performance of the code. So consider that we have the translation of the following 2 statements. A is equal to B plus C, B becomes E minus F, and suppose that all my variables exist in memory. Okay, so I can actually load the value of, so we load the value of B, we load the value of C, we do an addition, and then we store the result in A. But all of these variables exist in memory. So here, suppose that S0 here contains the address of A. Suppose that these variables exist in memory, one after the other. So here, for S0 will be the address of B. So we load the value into T0. 8 S0 will be the address of C. So we load here into T1. We do the addition, add T0 plus T1, put the result in T2, and store T2 at 0 S0, which is the address of A. Repeat. Okay, let us load the value of E, the value of F, do the subtraction. So load word, subtract, store word. Okay, very simple code. Okay, so 16 plus S0, this will be the address of E. So we load the value of E into T3, 20 plus S0, this is the address of F. So load the value of F into T4. Do the subtraction, put the result in T5, and store T5 at 12 S0, which is the address of D. So we are loading from memory, we are doing the computation, and then we are storing the result in memory. Now notice that how we have here the data dependence. So notice that the add depends on the previous load, and the subtract depends also on its previous load. So this is going to create a stall cycle. Now, if we have this code, the pipeline is going to work properly. Yani, even if we have this code, the pipeline is going to ensure the correct execution of these instructions. But what we can do here, okay, in the software is that to avoid these stall cycles, so there is nothing wrong with stalling the pipeline. The pipeline will stall, it's going to produce correct results, but we can improve the performance of the pipeline by changing the order of these instructions. So this is called scheduling. So this can be done by the compiler. So the compiler actually can move these two load instructions early in the code to avoid stalling the pipeline. So this will not really change the correctness of the code. So the code will produce exactly the same results, but it created some distance between the load and the depending instructions. So here I'm showing there is a stall cycle. So we waste one clock cycle. There is also a stall cycle. So there are two stall cycles in this example. Now here the software, and I compiler. Okay, the compiler can do scheduling of these instructions. And the meaning of scheduling, it means it can reorder these instructions without changing the meaning. Now notice that loading the value of E and F has nothing to do, okay, with the computation of B plus C and storing the result in A. So these two load instructions, let me just use here, okay, my pen tool. So these two load instructions here can be moved up before the add instruction. They can be moved here. So this is called rescheduling. Okay, rescheduling, it means reordering, okay, the instructions. So this can be done automatically by the compiler. So the compiler can do this, okay, and by doing this, okay, it can notice that how it has rescheduled, okay, the instructions, has reordered, okay, these instructions. It does this without violating data dependencies. So in this example, it's okay to move the load instructions, okay, up, okay, before the add instruction, and by doing so, we still have this add depending on this load. Okay, notice that we did not eliminate that. We still actually have this read after write, and also this subtract also depends on this load. Notice the value of T4 here. T4 is being read after it has been written. Okay, so we did not eliminate the data dependence, but we created a distance between these dependent instructions, and because of this, the pipeline will allow these instructions to move into the pipeline without stalling. So therefore, there are no stall cycles, okay, in the after rescheduling, okay, and reordering these instructions. So this is the advantage of here. The software can play a role. The compiler writer, of course, has to understand the pipeline, and of course, compiler writers have a good understanding of the architecture. In fact, they know it very well. And when they translate the code, they know exactly how the pipeline works, and okay, they can do something about it. Okay, so that's faster. Okay, so this is called here code scheduling, and it means reordering the instructions in the code, okay, without violating the data dependencies. We still have the same data dependencies, but the code can run faster, and we eliminate the stall cycles. Okay, is this clear? Any questions about this?
Yeah, it's clear.
Okay, right. So now we have other types of dependencies, which are called name dependencies. So what we have seen the data dependence, which is a true dependence, but we have something which is called an anti-dependence. Okay, this is called anti-dependence. And this means that we have a write after a read. So notice that here we have instruction J coming after instruction I in the program order, and J wants to rewrite T1 after it has been read by instruction I. So that's the opposite of data dependence. There is no data dependence here. It's called anti-dependence. And notice that we have here a write after the read. We don't really have a read after the write. It's the opposite, write after read. So we are reusing, instruction J is reusing T1. Now, there is no harm of doing something like this, okay, in a program, and this does not create any data hazard. I just wanted to mention that this is called a name dependence because we are reusing the same name. The name here is the name of the register T1. And we are reusing this register T1. So we do this a lot in programming. We reuse registers. So it's not a data hazard, okay, in the 5-stage pipeline. Why? Because we read in stage, notice that this instruction I is going to read T1 in stage 2 of the pipeline, while we write in stage number 5. So we can guarantee that T1 is read before by instruction I, before it has been modified and updated by instruction J. So because this is guaranteed, so it's not a data hazard in our pipeline. Okay, so remember that the read will take place in stage 2, while the writes will take place in stage number 5. That will be the write back to the register T1. And therefore, the instructions are processed in order in the pipeline. And because of this, this is not a data hazard. Okay, so it's called anti-dependence, or it's called write after read. And it does not really create any problem. Now, in more advanced pipelines, in which I'm not going to cover them in this course, I cover them in more advanced course, the 403 course. Okay, we can actually have advanced pipelines in which the instructions can execute out of order. Okay, then in this case, we have to be careful, okay, not to write T1 before it is read. So therefore, the anti-dependence can become a hazard if we allow instruction J to complete before reading T1. Okay, so if we allow J to write to T1 before it is read by instruction I, then this can become a hazard. But in our simple 5-stage pipeline, it's not a data hazard, so there is no need to worry about it. Now, if you would like to eliminate, okay, this name dependence completely, use a different name, as simple as that. So rather than instruction J using T1, it can use another register. For example, it can use T5. Now, T5 here is not being used. If you use T5, you have eliminated this dependence completely. And if you would like to have a more advanced pipeline, you can allow even instruction I and J. There is no dependence at all between I and J. You can even allow them to execute and to complete in parallel. And if you would like to have a superscalar processor in which 2 instructions can execute during the same cycle, and 2 of them can write back during the same cycle. Okay, this can be done if the instructions are completely independent. So if you use here, for example, T5, you rename this register as T5, then I and J will be completely independent, and therefore they can execute even in parallel, okay, or in whatever order. Yeah. Right. So that's known as a name dependence. There is also another type of dependence, which is called output dependence. Output dependence, it means that when you have 2 instructions, I and J, they would like to write to the same register, for example, T1 in this example. So I is writing to T1 and J is writing to T1. So both I and J are writing the same register. Now that's called an output dependence. Okay. Now, in our simple 5-stage pipeline, it's not a data hazard. Okay, why? Okay, why it's not a data hazard? It says here, all writes are ordered. Okay, and always take place in stage number 5. So the pipeline will guarantee that the first instruction here, which is the subtract instruction, is going to write back first. And then after that, the add instruction is going to write back to the same register T1. So therefore, the writes are ordered because the pipeline is going to execute and complete, write back the results of these instructions in program order. So therefore, we can guarantee that the write will take place after the write. We are writing to the same register. Okay. Now, can this happen in programming? Yes. Does actually I and J have to be just immediately after each other? No. Okay, we might actually have some instructions in between, fine. But we can guarantee that even if we write something like this, okay, then we can guarantee that instruction J is going to complete after instruction I, and the final value of this T1 will be the value of this add instruction, okay? So for this reason, it's not a data hazard in our simple 5-stage pipeline. But can it be a hazard? The answer is yes. I will not really go into these details. If we have a complex pipeline, okay, so in more complex pipeline, instructions I and J might complete out of order, okay? And this is actually the case in some today in modern CPUs. They have actually very advanced pipelining, and because of this, it can become a data hazard, okay? So in our 5-stage pipeline, again, it's not a hazard, it's not a data hazard, but it can become, you have a complex pipeline. If we allow instruction J to complete before instruction I. So if these complete out of order, and I write to T1 out of order, then the final value of T1 will be the value of the subtract, not the value of the add. Whereas according to the programmer, it should be the last instruction that is writing T1, which is writing T1, is the add instruction. Right. So can we eliminate this name dependence? Can we eliminate the output dependence? Can this be eliminated? Students?
What do you mean eliminated?
Can we remove this name dependence? Can we eliminate this write after write?
We change the name of the register, number of registers.
Yes, exactly. So we are using T1 here, right? So why not use, for example, T5 by renaming? So this is called renaming. So if we rename T1 to something else, it does not really change the meaning of the program. Yani, for example, if I choose here T5, then in this case, I can make them completely independent. I can even execute them out of program order or in parallel at the same time. If I have, for example, 2 ALUs, we can execute I and J in parallel. We can actually have a more advanced pipeline, a more advanced CPU in which we allow instructions to execute in parallel at the same time. They can also write in parallel. So as long as so we can eliminate this dependence completely by choosing a different name here, okay? A different register. And if you use a different register, then we have eliminated the write after write, and these two become completely independent, okay? So dependence here depends on the use of registers in the program, okay? Now, whether this is a hazard or not, depending on how you implement the pipeline. So we have seen that anti-dependence and output dependencies, okay, these two types of name dependencies are not hazards in our simple 5-stage pipeline because we force all the instructions to execute and complete in program order. And the write back takes place in the last stage of the pipeline. So we can guarantee that instruction J, which is this add instruction, is going to complete and write back T1 after this one. So there is no need to do anything about it in our simple 5-stage pipeline. But I'm just mentioning it. Okay? I'm just mentioning it that this is a name dependence. Now, how about read after read? Notice that here, for example, instruction I is reading T3 and instruction J is also reading T3. What do you think? Read after read.
It's not modified.
There is no problem here.
Yeah, there is no problem because we are not writing. Exactly, exactly. So read after read here, it says at the bottom here, read after read. It's not a name dependence. Why? Because we are not really writing. Read them in any order that you want. Okay, right. So I'm mentioning this because really in the next course, I go into these details and I show okay, more advanced pipelining, more complex pipelining, in which we can do a lot more, okay, inside the CPU. And this is actually what we have today in a modern Intel CPU, for example, or an ARM CPU. They allow these instructions even to execute in parallel, okay, or even to complete out of order. That's very interesting. So today, actually, modern CPUs allow this, and they can extract more and more parallelism, okay, from the program. Okay, so this is called instruction level parallelism. Anyways, okay, so that's the meaning of name dependence. We don't really have to worry about it in the case of our 5-stage pipeline. The only type of dependence is the true data dependence, is the read after the write. That's the true data dependence. This is the only type of dependence that we need to worry about. The name dependencies can be eliminated completely with renaming. Use a different register name here rather than using T1. Use, for example, T5. This register here can be renamed. If you use a different register, khalas, we have eliminated the dependence completely. The name dependence can be eliminated. It's a simple thing.